everything should be fine. Okay. So basicity of organic compounds now. Our objective, we must explain the differences in basic character of aliphatic amines, amides, and aromatic amines. We must explain the difference in basic character of the aliphatic amines, aromatic amines, and amides in terms of their inductive and conjugative effects. And we must explain the acid-base properties of the amino acids or zwitterions. But it's gonna be the next PowerPoint actually, right? So we're only doing 1 and 2 now. We know what the amides are, right? Do we know what amides are? Don't leave me hanging.
Yes,
What are
sir. We know
amides?
it.
Yeah, but okay. You see, each time when I ask you if you know what something is, just prepare to answer what it is. So what are amides?
So it's when it has like a nitrogen in it. Wait, no, I think it's like a N8. Never mind, guess it.
Well, then never mind. You have no confidence. Come on now.
Is it like a functional group with the nitrogen atom with a lone pair?
With a load. Hold on. I mean, sure. Oh my, hold on. This is what?
So
The second to last topic? Go ahead.
amide or amine,
Amide.
isn't it like one of those carbonyl compounds that CO double bond with CO double bonded and a NH2 group?
Bonded to the carbon in the carbonyl group, right?
Yeah. Yes,
Yes,
sir.
most definitely. That is what an amide is. You'll find amides. Why is my oxygen always beside the double bond? You'll find your amides looking something like this. Yes? You find it looking something like this, and then you have your entire carbon chain going on both its life. Right? Your R group. So this is your amide. And your amines are just NH2. And then your R group. It's really similar to one of the major amides that we talk about, because proteins are just amides. So when we reach macromolecules, we talk about it. That's all proteins are. And we can actually make proteins and carbohydrates and all those things that your body makes. We can make them in the lab. Right? We can recreate life. We're gonna talk about that later. So basic character of aliphatic amines. Aliphatic means it in aromatic, by the way. That is the opposite. It's the opposite actually. Aliphatic means it's not aromatic. That's simply what it means. Okay? So the basic character of amines, they are weak bases. Oh my gosh. They are. Alright? It's revolutionary actually. The position of the equilibrium is lies to the left because for weak substances, their equilibrium tends to lie to the left, right? As it relates to basicity and acidity. For example, methylamine, or what we call aniline. I'm sorry, not aniline. It's actually not aniline. It's actually methylamine, right? I'm jumping the gun here. I actually just started to think about aromatic compounds because they're my favorite. So, methylamine, right? Reaction with water would actually create a methyl ammonium, right, and a hydroxide ion. So they're bases because they tend to create hydroxide ions in solution, and we know that is a characteristic of our Arrhenius base. So it is an Arrhenius base. And as it relates to Lewis structure, what is it? Is it a Lewis acid or a Lewis base? A Lewis acid is an electron donor, yes? Yes?
No, sir.
No. Ooh. You sure? What is a Lewis base?
Lewis base is an electron donor.
Donor. Lovely. Right? So notice, that the nitrogen is donating its electrons to this. Alright? So, to the hydrogen specifically, right? In order to create the methyl ammonium. Right? So the methyl ammonium here. Methyl ammonium hydroxide. That is our substance here. Alright, so they react with acids to form salts as well. They do act as bases. So methylamine plus our hydrochloric acid creates methyl ammonium chloride. Easy to see, right? easy stuff. Starting off with the easy stuff. Basic character of aliphatic amines continuing, right? Remember that the values of the pKb now, we're talking about pKb and not pKa, gives us the information about the position of the equilibrium. The lower the pKb value, right, is the further the position is to right, the equilibrium position is to right in favor of the products, and the greater the basicity of the amine. So let's look at the basicities of these amines. Ammonia, which is our first amine, that is our where we get our amine derivatives from, right? We have methylamine, dimethylamine, and phenylamine, right? So based on the pKb's, which one is the strongest? Based on the pKb, which one is the strongest base?
Dimethylamine.
Dimethylamine, lovely. Alright, so this is 3.3, right? Then 4 points, well, then 3.4 for methylamine, then 4.7 for ammonia, and then 9.4 for phenylamine. Alright, so let's look at this, right? So two factors, right? Two of the factors that influence the strength of a base are the ease with which the lone pair picks up a hydrogen ion. Alright, so how easily donatable is our electron pair, and the stability of the ion being formed, right? So we always look at those type of things. So the strength of a base, weak or strong, right, depends on how easily it accepts a proton. A base having a greater tendency to accept a proton will be more strong, right? Will be stronger. In the case of methylamine, right, let's look at methylamine over here versus ammonia, right? Methylamine specifically has the presence of an alkyl group which increases electron density on the nitrogen. Why? Because of a positive inductive effect. Alright? Due to the increased electron density on the nitrogen, right, it can easily donate a pair to accept electrons. If we consider ammonia, there is no methyl group influencing the donation of the protons. Right? Just note that. So let's look at this, right? Specifically. In the methyl ammonium ion, the positive charge is spread around the ion, right, by the electron pushing effect of the methyl group, right? And the more you can spread your charge, right, around, the more stable your ion becomes. In the ammonium ion, there isn't any way of spreading the charge, right? So let's have a look at the ion specifically. Alright? So in the methyl ammonium ion, we can actually have an inductive effect moving electrons to minimize this positive charge we see here, right? But in the ammonium ion, there's no way to actually, there's no methyl group, there's no alkyl group, right, to actually diminish any charge, so they just stay with the charge. Alright? You can see that? You guys can see that?
Yes.
So while methylamine is a primary amine, ammonia is like, it doesn't have any alkyl groups. So in order to really look at it as reactants, the nitrogen is more negative in methylamine, right, than in ammonia. So it picks up hydrogens more rapidly. So as we saw here, it's more negative because the alkyl group is going to be pushing more electrons there, and it's going to be less negative in ammonia. All right. But with product formation now, the ion formed methylamine is actually more stable, right, than the ion formed in for ammonia, right? And so it's less likely to shed the hydrogen ion again. So those two things exemplify the fact that methylamine is a stronger base than ammonia. So not only methylamine having the power, right, or a more available electrons to actually donate, right, than ammonia itself, but when it creates its ions, methylamine actually has the ability to stabilize itself while ammonium cannot. Alright? These are the things that we need to be talking about when we talk about basicity. availability of electrons and stability of the conjugate acid. All right, those are some things that we need to focus on. Any questions? In the interest of time, going to be moving. Methylamine is a stronger base than ammonia because of the positive inductive effects on the methyl group. Secondary amines have two alkyl groups, and so they are stronger bases than the corresponding primary amines. For example, dimethylamine is a stronger base than the methylamine because it has two positive inductive effects. So if you check the pKb table, right, dimethylamine is stronger than methylamine. And that pKb change is because dimethylamine has two methyl groups over methylamine, which only has one. So you can clearly see that. So the first slide was trying to getting you to understand the fact that the presence of a methyl group actually makes the base stronger. And the more you have, the stronger the base. Because the more methyl groups you have, the more they donate, right, electrons to the nitrogen, the more they increase the availability of the lone pair on the nitrogen, right? So nitrogen is more and more, as you add more alkyl groups, it's more and more available to attach itself to a hydrogen. A base is a hydrogen acceptor. That is what it should do. And then when it accepts that hydrogen, because it has multiple methyl groups or because you have multiple alkyl groups, right, you are easily stabilized, right? Because the nitrogen will actually become positive and the alkyl groups will continue to push negative charge onto the positive, right, to diminish the positive charge. So the more methyl groups you have, the more basic the substance is. So the more basic the amine is, rather. So I don't want it to apply to any substance. The more basic the amine is. Right? Okay. Why is phenylamine a very weak base though? Alright? We have to understand why phenylamine is a very weak base. Phenylamine is a very weak base compared to ammonia and the alkyl amines. This is because of the conjugative or the resonance effect. In the phenylamine molecule, the lone pair of the electrons on a p orbital on the nitrogen itself, right, the nitrogen atom, overlaps with the delocalized electrons in the ring. Same thing like what's happening with the acidity. An extended delocalized system is formed that includes the nitrogen atom. Right? So what's happening there, you can see clearly with the green orbital here, it gets sucked into the ring, right? And anything we know about organic bases, electrons must be available, right, to attract a hydrogen because a base is a hydrogen, well, a proton rather, acceptor, right? Since the electrons are participating in the ring, it is not available, right, for the acceptance of the proton, and that makes it a weak base because the resonance effect or the conjugative effect makes it so hard for the base to accept a proton. And if it is hard for a base to accept a proton, it is a weak base. The harder it is for the base to accept the proton, the weaker the base. Alright? Because of the resonance effect, the electrons are participating in the ring and are not available for proton acceptance. Right? So that is the issue with phenylamine, and that is why it's a very weak base. Any issues? Are there any issues? We sure there are no issues?
Yeah, this was rather a simpler concept to grasp than the acidity.
Okay. Much simpler. Alright, that's lovely to hear. So it's simpler. Alright. So it's really simple. So let's looking at this now, the increased conjugative effect stabilizes the phenylamine molecules. The greater the the conjugative effect is greater than the inductive effect that you will see. Because some persons tend to say, hey, nitrogen is the most electronegative element in this entire compound. So why isn't it that... Wait, why is my pen not penning? Come on now. You know you want a pen. Alright. So if we're saying that nitrogen is the most electronegative, right? Why isn't this more effective, right? Right? So because we know that electrons are supposed to be traveling to the nitrogen, right? The resonance of a benzene ring overcomes that inductive effect that you see there. Because the inductive effect would mean that, it would allow electrons to be more available. Let me put the electrons there, the lone pairs, right, to be more available. But that's not true. In this case, it's not true. It is true overall, in aliphatic amines, but not in aromatic amines. Because in the case of phenylamine, the ring system is way stronger than that inductive effect. Resonance trumps the inductive effect. Alright? So it's all up to that. And you need to speak about these things when you're answering these questions. Right? Don't just talk about the resonance effect and everything like that, Right? They'll obviously see that the student doesn't know or overlook the fact that nitrogen is the most electronegative element in the entire ring or in the entire molecule. Alright? So you need to note that. You need to tell your examiner, right? You need to tell the marker that you know that nitrogen is the most electronegative element, and even though there's a positive inductive effect, right? The resonance system or the resonance effect is stronger than the inductive effect in this case, right? And that is how you tell them that phenylamine, right, is a weak base. Explain it to them. Let them know the system overlap and the creation of an enlarged delocalized system. Right? To let them know everything. I know the persons who just want to see equations and just work them out and run down about them business are probably not liking these topics, because this requires you to completely understand it, right? And be able to write paragraphs explaining this. You need to be able to write paragraphs explaining these things. Alright? 12 marks just don't come out of thin air. Alright? So we need to know these things. For amides, however, these are much weaker, right, bases than amines. Why is that? The conjugative effect, of course. The amides possess a carbonyl group. Therefore, it can be resonance stabilized between the double bond existing CN or CO. It is possible, right? So amides are neutral to litmus and do not react with hydrochloric acid to form salts. Yet they're basic. They don't undergo basic stuff, right? Or things that bases are known to undergo, right? Yet they are slightly basic. A p orbital on the nitrogen atom interacts with the p orbital on the adjacent carbon atom. There is a considerable delocalization between the oxygen, carbon, and nitrogen atoms, which does not occur in ammonia or alkyl amines. Right? This reduces the ability of the lone pair, right? The availability should be the availability on the lone pair, right? Or the ability, in this case, of the lone pair on the nitrogen atom to accept the proton, right, from the water. So looking at this now, we're talking about the availability of the lone pair now. But if we're going to have an amide like this, shifting the electrons all over the place, constantly between carbon and oxygen and between carbon and nitrogen, it's not going to be as available as we want it to be for it to accept a proton. And what do bases do? Bases accept protons. So if your electrons are not there, if your electrons are busy participating in conjugation, right, it's not going to work out for you as a good base. It's not going to be good for you. A good base has their electrons sitting right there waiting. If your base continues to move your electrons in resonance effects, right, or resonance systems, you are not a good base. Because your electrons must be in one place, centralized charge, ready for the acceptance of a proton. If it is not in one place, but a run up and down in a one ring, right, or a run up and down between pillar and post, right, within these types of resonance effects within amides, it is not a good base. Bases depend, organic bases rather, depend on the availability of that lone pair for the donation of electron or the donation of a lone pair rather. Alright? That is what it must happen. It is a Lewis base. It is a Arrhenius base. It is a Bronsted-Lowry base. Alright? So these are bases. Okay? So hopefully that is understood, because that is the end of the topic. Hopefully understood, because that is the end of the topic. And at the end of the day, this is your gift, right? So the gift you always wanted is right here. With the aid of an equation, explain the basic nature of ethylamine. The pKb values for B, the pKb values of phenylamine and ethylamine are 9.38 and 3.33 respectively. Firstly, state what information does the pKb values give about the strength of a base, and account for the difference between these pKb values of phenylamine and ethylamine. And the last part, ethanamide and ethylamine are aliphatic nitrogenous compounds. Ethanamide is almost neutral and has a pKb value of 15. Alright? Explain the difference between the basic property between ethanamide and ethylamine. So these questions we should be able to do.